So thank you, and thanks to the rest of the organizers for inviting me. As is usual when preparing the first few minutes of a talk like this, I went back and looked at my old records. So I was first in Singapore in 1999. And I must say I've sort of enjoyed coming back every time. So thanks for that. And I also checked when I first met Ted. So that was in 1980 when he was a graduate student at Harvard and I was visiting at MIT. I have to say I didn't really get to know too much about him that semester, but our collaborations and conversations developed over the years and over time. Our first joint paper was in 1989. It came out of work that based on a talk that he gave in Ithaca. And I've enjoyed the collaboration over the years and the conversations and friendship, and I'm very happy to be here speaking and being able to welcome Ted to the group of people in whose honor one holds meetings at a certain age. The choice of topic here is also, well, obviously this is a joint paper with Ted and with Leo as well. It's our, I won't say our last, but our most recent collaboration. And the work on it began at a previous meeting here in Singapore at the IMS. So and in addition had the feature that it's actually about the topic announced for this meeting. I mean, when I was first invited, I said, well, I'm not currently working on anything in hyperarithmetic theory. And Yang Yui said, well, it doesn't matter, whatever. But then I realized, oh, well, I did have this paper that's not too long ago. And there are some new applications of the theorems in it that I'll speak about. So I decided to choose something about the topic of the meeting as well as about involving Ted. So another motivation was that the sort of newer material involves applications to subjects I don't really know much about, and in model theory of non-classical logics and modal logics, and included in some other areas of that sort. And I'm hoping that someone in the audience will tell me if this is of any interest to anyone else in the world. And I'm also hoping that there'll be applications in descriptive set theory that people here might tell me about. So now, as a previous speaker said, what Ted would really like is to get to the mathematics, but here maybe less so since he knows this already, as the case with many other talks. I guess there was one other point about our collaborations that I wanted to mention, was that, so this is, as I said, our most recent, our 13th joint paper. But looking back at my old records, I realized that this should have been our 14th, because I have one paper still on my list of old works not yet written up. Now, many papers have fallen off that list, not because they were written, but they just were never going to be written. A few, for sentimental reasons, I keep on that list. And one was a very early paper with Ted. And I won't tell you who was supposed to write it up. So this is our 13th. So we're going to essentially work in Cantor space. And we use the standard notation and normal forms, which there they are. And so sigma 1, 1 in a real means expressible in a certain kind of formula, sigma 1, quantification, and we'll use the typical normal forms, and a class of reals has the same sort of kind of definition. So we have two theorems that are the same except for what level they're at. And the first one says that if you have a real, which is sigma 1 in every member G of a non-empty sigma 1 class of reals, then it's sigma 1. Now, when we proved this, we thought this should have been a well-known theorem 40, 50 years ago or something, but it seems not to have been. And it has corollaries, many theorems that were known 50 years ago, but not this one. And then the same theorem is true for classes of reals. In all honesty, I should say that's Leo's part of the paper. The proof of the first theorem is easy, and the proof of the second theorem is hard. So this theorem, I don't know if it looks like a basis theorem, but it is a basis theorem, if you rephrase it in certain ways. It also is a type-emitting theorem, if you look at it in certain other ways. And it's also a forcing construction, as we may or may not see depending on time. So here are a couple of classical basis theorems. So here's the Gandy basis theorem. Basis theorem says you have a collection of objects, here a non-empty sigma 1 class of reals, and then you say it has a particularly nice element. Here a Z such that has lowest possible omega 1 ck. The ordinals recursive in it are as small as possible. Another one is a Kreisel basis theorem. If you have a non-hyperarithmetic real, it's not delta 1, and this K is a non-empty sigma 1 class, then K contains a real Z in which X is not delta 1. So a nice member. Another way of looking at the second theorem is that it says that if X is hype in every member of a non-empty sigma 1 class, then it's actually hype. Okay, well that's the same as our theorem, except that we've improved delta 1 to sigma 1. And the theorem also immediately gives the Gandy basis theorem if you know one or two simple facts from hyperarithmetic theory, namely that O is not sigma 1. And so there's a member of the class in which O is not sigma 1. And Spector, by an old result, all of these results are old, right? Even from my point of view, before my time. That Spector showed that this gives you the result on the ordinals. Okay, there was after we proved the theorem, I sort of went looking in Sachs's book and said, what other corollaries are old theorems? And there were several. Well, I guess I'll list them later, but I'd like to, at this point, put in a remark that Sachs gives after he proves all these theorems using techniques of hyperarithmetic theory. These are frequently theorems of Kreisel. And he says that all of these theorems are about sigma 1 sets, and he says that they look like type-emitting or completeness constructions in some kind of different logic. And he says that the recursion theorist winding his way through a sigma 1 set is a brother to the model theorist threading his way through a Henkin tree. Maybe a little mysterious. So our proof, which implies all of these theorems, doesn't use any hyperarithmetic theory, doesn't use any model theory. And it's a proof that is a forcing construction. And so we found a third sibling who was doing the same work, but sort of traipsing through a forcing construction and reaching the same conclusions. And it actually doesn't really use any forcing material either, just the definition. It's a very simple proof. I mean, it uses the word forcing, but no non-trivial facts. So now, given this, it's not surprising that there were other manifestations of this that, well, that I wasn't aware of them maybe isn't surprising either, but when I talked about the result to various people, one of whom is here and one of whom is left, they each told me some other thing that was just like it. So Steve Simpson said, oh, that Uri Andrews and Joe Miller, who I guess is here. Is that nice? He's okay. More important things. Had proven us the same theorem, but instead of about sigma 1, 1, they had proven about pi 0, 1 classes. So thinking about it a minute, it was not surprising. They used pi 0, 1 class forcings, and we had used sigma 1, 1 class forcings, known as Gandy-Harrington forcings. So they proved the analogous theorem at the pi 0, 1 level. And John said, oh, well, at sigma 1, 2, this is a classical result if you, again, look at it the right way. Oops, that was back. There's a basis theorem at the sigma 1, 2 level that every sigma 1, 1 non-empty sigma 1, 2 class contains a delta 1, 2 real. And then trivially, since anything sigma 1, 2 and a delta 1, 2 real is sigma 1, 2, then the same theorem holds for the sigma 1, 2 class. On looking at the titles for the upcoming talks, we're apparently going to find out about some sigma 1, 3 basis theorem, which I suspect will be nothing like, whose proof will be nothing like the proof of these. Yeah, I'm sure Hugh will. That's right, Hugh. Nothing, not a simple forcing argument. Well, maybe. So here are some other applications of the theorem for reals. And these are the ones that prompted the remark of Sachs. So these are all theorems of Kreisel that talk about models of comprehension or of choice, and the minimal models of these axiom systems sometimes with other constraints. And they turn out to be hype. And then he has a sort of a more general, Kreisel had a more general theorem. If you have a pi 1, 1 collection of axioms in second order arithmetic, and a real belongs to every countable omega model of that axiom system, then it has to be hyperarithmetic. That the other things are examples of this is not hard to see. So, but all of these are immediate corollaries of our main theorem. Why is that? Well, what does it mean to be an omega model? That means you have something that looks like an ordinary first-order logic, but some part of it is isomorphic to the natural numbers. Okay, well, how hard is it to say that it's isomorphic to the natural numbers? It's sigma 1, 1. So the class of models that are described in each of these applications, each of these theorems, old theorems, is a sigma 1, 1 class. And any member of the model is recursive in the model. And so it's any real in every model is sigma 1, 1 in each of the models. And they're closed under complementation because it's a model of trivial parts of arithmetic. And so they all follow from the main theorem. Okay, so what happened here? Well, the last theorem was a theorem about omega logic. And it said that if you read it in the right order, that you could get a model that didn't have some set in it. If the set wasn't sufficiently simple, you could leave it out. Well, that's a type emitting result. And the only thing that we needed was that sort of the class of models were sigma 1, 1. Well, there could be a lot of logics and theories for which the class of models is sigma 1, 1. So we'd like to give some sort of general version, or maybe lots of specific, maybe we've already given the general version, but lots of specific instances. So you want to define what a type emitting theorem is. So we have a set of formulas gamma in some language yet to be specified, in some kind of logic yet to be specified. And they're closed under trivial things like change of variables, and some nice collection of formulas. And what is a type going to mean? So we have a subset of the formulas in gamma, which have the same free variables. So it's an n type. The free variables of every formula in this collection are x1 through xn. What does it mean for it to be realized in the model? Well, it's the usual definition, that there are elements of the model which, if you plug in those elements for the free variables, then the formulas in the class that are true of those elements is exactly this type P. So that's what it means to be realized, and omitted means it's not realized. This isn't quite the standard definition of a type, but it's slightly more general. Okay, so what's the first generalization? The immediate generalization of omega logic is that, well, just look at a two-sorted logic where you have sorts n and m. And this is in the usual way, you think of it as having predicates for the two sorts, and some structure or language in each sort, some part of the language is combining the sorts, whatever the syntax is. But we can make it into a non-first order logic by saying that the first sort has to be isomorphic to some fixed countable structure in the appropriate language. The standard example is being either arithmetic or the ordinal omega. That gives you two different versions of omega logic. But there's really no reason for it to be omega. Just any countable structure will work. But the same theorem is, of course, true. So if you're an n model, so your first sort is isomorphic to n, that's a sigma 1, 1 fact. And then you want to satisfy some theory. Well, how complicated could the theory be? Well, for every formula in the theory, you're true. So if the theory is pi 1, 1, then for every formula in the theory is sigma 1, 1. And then you just have to check that your semantics is no worse than sigma 1, 1. So the same corollary works for any example of n logic, for any countable structure. Again, if someone knows already studied examples for where you assume the first sort is the rationals, or any structure at all, I'd be happy to find out. I haven't searched. It's hard. I don't know how to search for this even. So we've basically given the proof. The only thing is you have to check that you can make, if there's any model, there's a countable model. Well, that's a Skolem-Lorvenheim theorem. And then you have to check that the semantics is correct. That is, being realized means that the set of things that are the formula is satisfied by some particular finite sequence is a simple set. So that's all there is. Okay, but now if you think of this if this is a type emitting theorem, then there's no reason why if you can emit one type, you should be able to emit a sequence of types. I mean, I don't know, that's always true, I suppose, or maybe not. So, but you can do that. What's the version of the theorem? Well, you're just given a sequence of reals x, none of which is sigma 1, 1. Then you can get some member of your non-empty sigma 1, 1 class so that none of the x's is sigma 1, 1 in G. And by thinking about complements, if no x is hype, it's delta 1, 1, then there's a G so that no x is delta 1, 1 in G. So now you can relativize, there's a recursion theory theorem, so you can relativize it. So I mentioned this particular corollary because it was sort of the motivating fact that in some sense led to the theorem, as we wanted to use this fact, which we knew must be true because of Barwise or something, but we were thinking about it, Ted and I. And so here's the corollary. So if you take a real C and a sequence of reals xn, which aren't type in C, then there's a countable omega model of ZFC containing C, but not any of the xn's. And the well-founded part, you can control the ordinals. You can control the well-founded part. The well-founded part is the smallest possible. Well, if it has C in it, then it's got to have the ordinals recursive in C, and it doesn't have any more. So the well-founded part is exactly omega 1 to the C. And the proof is the same. Being a countable omega model of ZFC is, which contains C is sigma 1, 1, because having C as an element just says that there's a map of the appropriate sort, so it's sigma 1, 1. And now you apply the theorem, so you want to make sure that you emit the type of omega 1 to the C. Well, you just add on a new real to your sequence, which is O to the C, Kleene O, because so now you can get a model by the theorem, an omega model of ZFC containing C, but not containing any of the xn's. So it contains C, everything recursive in C, but it can't contain any ordinal bigger than omega 1 to the C, because then it would contain O to the C. Another old theorem of probably Spector. I don't know. So I'd now like to move to some other kinds of logics that we really hadn't been thinking about when we wrote the paper. And this is another one of these sort of serendipity events. So sometime after the paper, shortly after the paper was published, a new postdoc came to Cornell in the computer science department, Lior Cohen, who came from Tel Aviv and had been working in sort of things that are like philosophical logics. And she came to work in these logics from the computer science point of view. And I was talking to her about what she had been working on, and she described to me a whole bunch of logics and how she had been worrying about decidability issues and completeness issues, and that now she was supposed to study sort of applications to certain kinds of constructive logic. And when I was talking to her, it occurred to me that, well, the level that she should be looking at the questions was not sigma 0, 1 and recursive, but hyperarithmetic, that these were complicated logics. And I said, you could just as well prove, instead of having proven that it's undecidable, you could prove that it's not hyperarithmetic. And she didn't know what that meant. But she was interested. Then she went on into computer science. So after first asking for references, I don't think she ever followed up. But I kept thinking about it a bit. And I realized that, well, all of these logics had the same sort of sigma 1, 1 property. And that so we could prove type emitting theorems for logics for which no one had ever thought about type emitting before, I'm sure. I was sure until I found one old paper, but not on these logics. So let me mention some of these logics. Some of these are sort of well known. Some of these should be well known, I don't know. So there's weak second order logic. Here you restrict quantification, second order quantification to finite subsets. There's cardinality logic for aleph 0. That means you have a quantifier which says there are at least aleph many elements satisfying some formula, and aleph here is aleph naught. So that's countable cardinality logic. Here's one that maybe fewer people, some in the room will know, is ancestral logic. So here you add on a transitive closure operation as a new kind of quantifier. So you have the syntax by adding on this formula Tc x sub xy phi of xy uv. Okay, what does it mean? So this is, you're thinking of the formula phi has free variables, u and v, and it has variables x and y, and this syntax binds the x and y, and what it says is that the formula holds of a and b if there's a finite sequence that goes from a to b, such that at every successor stage you satisfy the formula phi. So you can think about this as if phi is just a linear order, is a edge in a graph, then this says that you're connected. But you can do this. The syntax works for any relationship, not just having an edge between them. So, but now, if you think for a short period of time, you say that, well, how complicated is the semantics here? Well, you want to call Skolem-Leuvenheim theorem. So you look at it and you say, oh yes, everything's countable. You have a Skolem-Leuvenheim theorem. Satisfaction is arithmetical in the model. So you now can prove a type emitting theorem for all of these logics. Same theorem. That is, if you have a pi11, get the right order. If the theory is pi11, then this set of formulas over which you're taking your type is sigma11 or sigma11 in whatever the given structure is. And you have a sequence of types, none of which is sigma11, then you can have a model which omits them all. Okay, next example. This is one that, so Antonio has a type emitting theorem for computable infinitary logic. I don't know, it's not this one maybe exactly. And I guess when I realized this worked, so I mean, you think of it as barwise, maybe you think of them in terms of barwise, but you can do the same thing here. There are some slight differences. So first of all, maybe if you don't know what computable infinitary logic, not everybody was at your talk, where you may be. So you allow conjunctions, disjunctions over countable, say recursive or recursively enumerable sets of formulas, and you build up through the recursive ordinals in terms of complexity. So now there's a little trickiness introduced because the set of formulas is not recursive anymore. And it's not sigma11, it's pi11. So being a formula is a pi11 property. Being a formula at some particular level of the recursive ordinal hierarchy is hyperarithmetic. Okay, so that's what the syntax and semantics are. But now, if you're a pi11 set of sentences in this computable infinitary language, then being a model for it is a sigma11 property. Okay, so now when we want to look at the set of gammas, so there's a slight restriction here. Since being a formula is not sigma 1, 1, you have to throw away the things that aren't formulas. So you have this, you say that your sigma 1, 1 on S means if you're equivalent, if you're the intersection, sorry, your sigma 1, 1 on the language, if you're the intersection of the language with a sigma 1, 1 set, which is the same thing as saying that if you throw in the things that aren't formulas, you're sigma 1, 1. Okay, for example, if you're only worried about formulas up to some level of the hierarchy, then that's actually going to be delta 1, 1. So now you have this same notion of being a type, and you have a type emitting theorem for computable infinitary logic, which is pretty general. Look, it reads the same, it's exactly the same theorem, just the words have slightly changed their meaning. Proof is the same. Here's the proof. It's the same, except for manipulating the fact that the set of sentences is not recursive anymore. That's what this says. So you check the manipulations. Okay, now I know there are people in the audience, because I've heard them using the words in the lounge last week. So there are people here who actually think about modal logics. So let's look at modal logics. So a quick explanation of what modal logics are. So here you have a language which has, say, the language of typical first-order logic, plus some extra operators, box and diamond, which are supposed to represent modalities. So like knowledge, I believe this, this is true, this is necessary, this is possible, this will happen in the future, all kinds of modalities here. And the semantics is Kripke frames. So it looks like W is a collection of what are called possible worlds. What a possible world is just is a model of the ordinary first-order language here. So for each P and W, there's a C of P, which is a classical structure. And then you have some accessibility relation on the elements on the worlds. That is, from this world, certain other worlds are relevant. And then you can say, aha, what happens in the future means that you can get to by your accessibility relation, or lots of other possibilities. Okay, so now, how about type emitting theorems for modal logic? So I said, why not? Just check this, just check how complicated the semantics is. Well, but now you can play with this in ways that modal logicians don't usually think of as accessible, because you're allowed to give restrictions on the class of models, not just in terms of the syntax of the first-order language, but you can directly say things that are not first-order about the accessibility relation. So you can specify, so if you're doing temporal logic, talking about time, you can specify that your model of time is exactly the natural numbers. Or you can say that it's, if you're talking about physics and you believe, you can think that whether you decide you believe quantum physics or not, you could say that your succession of space is the rationals or the natural numbers. So the modal logicians do talk about these classes. They're quite important for various applications, but this allows you to put into the collection of sentences for which you're emitting types, not only statements about what's true in each world, but also what's, is the usual terminology, forced at some world, forced at every world, forced only in frames in which you the accessibility relation satisfies certain properties. you have all these type-emitting theorems, which I thought no one had ever really thought about. I mean, I'd never seen a use of a type-emitting theorem in modal logic. This search actually turned up a paper in 1974, by someone named Mortimer in the JSL, in which he proves a type-emitting theorem for some kind of modal logic. If anyone knows of any applications of these, or of any instances, I'd like to find out. So here's the statement of what I just said on the slide. And again, you have a pi11 collection of sentences but the sentences could now talk about the accessibility relation and all kinds of other things. And you can do type emitting. So now the next thing that occurred to me was, oh, well, why not combine these two things? And let's do modal logics, in which case the possible worlds are described not by classical first-order logic, but by any of these other generalized logics that the computer scientists are now interested in. And why, it doesn't make any difference. The semantics at each world is still at the level we need. So you can now prove a whole array of type-emitting theorems about logics, which I think no one has ever thought about. So maybe someone should. I mean, maybe it makes sense to put in these other structures in your Kripke frames. Okay, so here's yet another logic that occurred to me, which I'd like to know if anyone has ever thought of, and if not, whether anyone has any use for it. Because this one actually talks about mathematical structures, which I call extension logic. So what's the syntax here? So you have first-order logic, or maybe something else, any of the other sort of generalized logics. Let's not try, not the modal ones. That gets very complicated. But and now you add in formulas which say that there are new second-order variables, and you say there exists R1 through Rn such that phi holds, where phi is a formula in the language with these extra predicates. What does that say? Well, what does it mean to have a model? Well, it means that you had a model of your first-order language, or one of these other languages, and you say you can extend that model by adding in new predicates which satisfy some formula or some theory. That is something that algebraists think about, that people think about. Like, can't you have some group or ring, can you extend it, make it some more complicated structure? So the semantics is the obvious one. But now we can prove a type-emitting theorem for this kind of logic. It's the same theorem. You have a pi11 set of formulas with a model, and you have a set of types, none of which is sigma 1,1. Then you have a model in which none of them are realized. What does that mean? This says that, you can look at some theories, some collection of models, first order, and you say, oh, every one of those models can be extended to a structure with an additional structure, and then you want to know, can then those extensions be extended some more? Seems like it should be a reasonable question. And this says that sometimes you can't. So it gives you criteria for saying when you can't make an extension to satisfy a whole new theory. So I'd like to know if there are any examples where this might apply. Okay, so I'd like to say a word first about complexity, about how hard it is to find these witnesses. So we said that you have this non-empty sigma 1,1 class, and you have some x that isn't sigma 1,1, then you can find an element in which it's not sigma 1,1. How complicated is that x? Well, that x is G, which probably people have realized already that it means it's a generic object. which you would have thought of. If you were thinking of leaving out omega 1 ck, then, or not computing something, then it must be a generic object that doesn't compute it. So, how hard is it? Well, if we had seen the proof already, then I would just say, oh, it's obvious. So I'll just say, if there's time, which there won't be, we'll see the proof and it will be obvious. But the theorem is that you can sort of, look, you're dealing with sigma 1, questions. Who knows the answer to sigma 1, questions? O knows the answer to sigma 1, questions. So in your construction, you're asking sigma 1, questions. Can you do something? Can you make this sigma 1 fact be true or false? And O should know the answer to that. So this G should be computable, should be recursive in O. And if you believe the basis theorems already, it should be strictly smaller hyperdegree. Because if that's what the basis theorems tell you. So that's the theorem. And the proof is that look at the proof and see that, yes, it works. So, for example, if you can get that O is not delta 1 in G, and so it has you can make it have strictly smaller hyperdegree. As long as the x's that you're trying to emit are not hyperarithmetic, then none is hyperarithmetic in G. So here's a typo I noticed this morning. So I want to use this calculation to give a common generalization of the Kleene basis theorem and the Gandy basis theorem, right? That somehow K at the beginning meant Kreisel, and now it means Kleene, but when it's written out in words, it actually says Kleene. But so, here, see, Kleene. So, having small omega 1 ck, having large omega 1 ck means that you can compute O hyperarithmetically. There are specific, more is true. So you can combine the Kleene and Gandy basis theorem. The Kleene basis theorem, which I didn't have up before, says that if you have a sigma 1, non-empty sigma 1 class, then you can compute a member recursively in O. And that's because O can tell you whether there's a path above you, and you just go through the tree. So that's Kleine's basis theorem. So here you have a non-empty sigma 1 class of reals. Then it contains an element which is both recursive in and of strictly smaller hyperdegree than O, and has, therefore, the right smallest omega 1 ck. Okay, so that's the end of our theorems about reals and sigma 1 classes about classes of numbers. I'd like to at least state the theorem again about classes of reals, because, well, first I'll remember it. So, if you have a class of reals, which is sigma 1, and every member of a non-empty sigma 1 class of reals, it's also sigma 1 as a class of reals. So the proof of this also uses forcing, Gandy-Harrington forcing, but I'm, sorry or happy to say that it actually uses the forcing. It uses non-trivial facts about Gandy-Harrington forcing and a number of theorems of effective descriptive set theory, and is several pages long as opposed to being a couple of paragraphs. So I had never any hope, right? Even at the end of the slides, there's no version of this. I have the proof of the first theorem in the slides. It only takes like 4 slides. When is this supposed to? Oh. However, if you wanted to go to this delta 1,1 version, as opposed to the sigma 1,1 version, then there is a simple proof, or much simpler than this one, like the original one. And it's one that extends to sequences. So if you have a non-empty sigma 1,1 class of reals, and a countable sequence of classes of reals, none of which is delta 1,1, then there's a G in B such that none of them is delta 1,1 in G. Okay. And there's a corollary, which is a kind of basis theorem. Any class of reals which is delta 1,1, and every member of a sigma 1,1 class of B of reals is delta 1,1. So I'd like to know for the descriptive, well, I'd like to know in general whether the simple proof generalizes to sequences. As far as we could tell, the complicated proof for sigma 1,1 doesn't. So that's annoying. So the theorem about delta 1,1 should be true for sigma 1,1, but I don't know a proof. And then, in contrast to the long list of applications of the theorem at the level of individual reals, I don't know of any applications in descriptive set theory at the level of classes of reals, but there must be some. So I'd like the descriptive set theorists to tell me what they are. Okay. So now, when am I supposed to end in 50 minutes or an hour? Am I supposed to end in 2 minutes or more? When is this supposed to end? What? More is okay. Okay. So the 2-minute version of the proof I've already given. Here's the more version. So what's Gandy-Harrington forcing? So the conditions are non-empty sigma 1,1 classes of reals, and with the usual, what you'd think the definition of extension is. So now, the only formulas we're interested in are sigma 1,1 formulas and their negations. And the definition of forcing at this level is trivial. That is, a sigma 1,1 class L forces a sigma 1,1 formula just in case the formula is true of every member of the class. Okay, and the forcing negation is what you'd think it should mean. There's no extension, which turns out to be the same as it's false for every member of the class. There's a little argument proving that. So now, how are we going to prove the theorem? What does the theorem we're proving say? So we're given this real x, which isn't sigma 1,1. So we'd like to build a generic G, and G should be a member of the class, and x should not be sigma 1,1 in G. That's the proof of, that's what you want to prove. So, well, okay, we have a list of the formulas that could define x, potentially. So now we want to do a forcing argument. This is the same as a classic simple recursion theory argument. That is, you have a condition, and you'd like to make your generic not compute some x. Okay, well, what do? Well, how would you want to diagonalize? The first thing you try is I diagonalize. So I look for an n. It's not here yet. This is more some technicality of how you do it. But, so we're going to do a construction where we're constructing not only the generic, but also the various witnesses for sigma 1,1 facts being true. And then there's a limiting process, and things will work at the end if you do it correctly along the way. But what is the idea of the construction? So you start off, and here you have a particular, never use this, right? Here you have a particular formula, and you'd like to know maybe it defines X or not. So you try to diagonalize. So you want to find the number M, which is in X, and you can force that the formula fails, or is out of X, and you can force that the formula holds. If you can do either of those, then you've diagonalized, and that formula doesn't define X, which is what you wanted. And this is the technical facts about how the approximations are extended to make it true at the end. So what could happen? Well, if you were lucky, and at every step of the way you were able to diagonalize, then you win. You've made sure that no sigma 1,1 formula in G defines X. That's what this says. Okay, so what happens if you couldn't do that? Okay, I can't force it to be different. Well, then what do you say? Well, then it must have been sigma 1,1 already for the contradiction. And why is that? Well, what's the usual argument? The usual argument is that, oh, well, I look for an extension which makes it defined at n. It must give the right answer, because otherwise I could diagonalize. And if there weren't any, then I would have won also. So there can't be extensions that give two different answers, because then you diagonalize. So there's some extension which gives an answer, and it must be the right one. Well, how hard is it to say that? How hard is it to recognize the fact that it gives the right answer? Well, searching for it is a sigma 1,1 process. I think that says this. Oops, sorry. So that's what it says. So if it fails, then you write down a sigma 1,1 definition of the set X you were given. That's the usual recursion theoretic other outcome, contradiction. Okay, so now that you've seen the proof, that was the entire proof in all detail on the slides. I mean, you couldn't really have read it, but it was there. So now, how do you get sequences? Well, you want to do the proof once. If you can do the proof once, you can do it countably often just by interleaving the requirements. So you just do that. That's the proof for sequences. Now you have to check it could go wrong in more different ways at different times, but it's the same proof. You have to worry about the extensions, everything fitting together. Oh no, now the question is, I claimed that if you knew the proof, you would immediately check the complexity. Well, what is it you did? You had to look for an M with certain properties. And how complicated is the property? Well, it either says that, and you look for an L, a sigma 1,1 class. I mean, that's just a formula contained in the previous one. That's a conjunction. And then you want to say that there's some member of the class which makes the formula true, or for every member of the class, the formula is false. Well, these are sigma 1,1 or pi 1,1 formulas. Well, who knows what the answer to a sigma 1,1 formula sentence is? Is it true or false? Well, O knows it. And he knows it uniformly. And he knows it recursively. And he doesn't need everything he knows to answer it. So that's the proof of the complexity argument. You just look at you have to worry about all the details, that they were even easier, of how you do the approximations. But that's routine. And now, the last bit of that theorem on the complexity was that he doesn't need everything. That the G that you build is actually strictly smaller hyperdegree than O. So how could O build something? That's not, what do you do? Well, we've already seen the answer to that in some sense, is just throw O into this list of X's. O is not sigma 1,1. So when you were looking at an arbitrary X, one of them was O, and you made sure that O was not hyperarithmetic in G, and therefore it's not. We made it not sigma 1, 1 in G, so therefore it's not hyperarithmetic in G either. So it is, it's hyperarithmetic in G, and O isn't hyperarithmetic in it, so it's strictly smaller hyperarithmetic degree, and that's the end of the complexity constructions. Okay, so thank you very much, and thank you, Ted and Hugh, for producing the reason for the meeting. I want answers, not questions. Yes.
I just want to point out one thing.
Yes.
Reading your paper, William Shannon, I noticed we can a similar result in the AD context with OD replaces sigma. There's every real set of reals that's OD in the set.
Right.
Set real is OD is OD.
Oh, good. By a similar.
So that version goes through.
That version also goes through. Okay, and the proof is similar. And
it's a forcing argument. It uses like a copenic forcing and AD plus.
Okay, good. Thanks, yeah. Okay, that was one answer.
Reals and percent of real data.
Yeah, both versions.
Yeah. I don't think they look at the sequence.
Okay, that, let me know if this, because if the sequence version works there, it should work. If it works, the sequence version works for sets of reals, classes of reals, and maybe there's some, think about that and tell me.